Alright, we have finally arrived at Unit 9, which is Stoichiometry, which is quite possibly the funnest word in the English language to say. If we break down this word, it will actually help us understand what this process is all about. So this root here comes from a Greek word stoichon, and it means element. And I gotta tell you, every time I say stoichon, I think of the little squirrel from The Emperor's New Groove. I hope you know what I'm talking about, otherwise this is embarrassing. And then metry means to measure. So if you throw those two together, we're measuring elements. Now that's something you did back in Unit 5 or 6 or whatever it was, when you did the mole. And so you learned the basis for these calculations, where you would take, say for instance, 5 grams of sodium, and you'd be able to convert that into moles, and then convert that into molecules, and convert that into atoms. You could do the same thing with something like oxygen, and even convert it into the volume, given the fact that it was a gas at room temperature. The thing about the mole unit, though, is if you're talking about NaCl, if you're talking about grams of NaCl, then you change that to moles of NaCl, and then formula units of NaCl, it's always NaCl. You're always just redefining one measurement using different units. It's the same thing as saying 1 foot or 12 inches or 1/5280th of a mile. It's the same distance every time. Stoichiometry takes those skills of going from moles to grams and grams to moles and moles to molecules, etc., and squishes it with our last unit, which was chemical reactions. So when we write a chemical reaction, as you recall, we have to know what the reactants are, what the products are, and then the finishing piece was always these balancing coefficients. Okay, so this is a balanced chemical reaction for the combustion of butane, C4H10. And in order to balance the reaction, in order for this to proceed, I would need 2 C4H10s, 13 O2s, and it's going to produce 8 CO2s and 10 H2Os. Well, yeah, that would work if I was talking about individual molecules, but we can also scale that up. Okay, so what these coefficients actually correspond with are moles. Okay, and that's how we're going to use them. So what this reaction says is, for every 2 moles of C4H10 that I react, I also need 13 moles of O2. And if I react those in that ratio, I will be able to produce 8 moles of carbon dioxide and 10 moles of water. So what this means for us is, by writing a complete and balanced chemical equation, what we've actually done is create ratios between all these different reactants and the products that we can use in dimensional analysis. So now, instead of just converting from grams to moles to molecules, etc., of one thing, I can say, hey, if I have this much of a reactant, how much product am I going to be able to produce? Or if I have this much reactant, how much of the other reactant will I also need? Or if I produced this much product, how much of the other product will I, etc. We can go any combination. As long as we use these ratios that come from the balanced reaction, we can do any calculation that we want to. So for instance, if we have 5 moles of O2 and they are reacted, okay, how many moles of carbon dioxide are produced? So this is what I was trying to say, is we're no longer going from moles of O2 to grams of O2 to just O2, 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 O2. Now it's, hey, O2 being turned into carbon dioxide, and in order to make that happen, I need this reaction, because that's what provides the ratios between the two. And you can see that already. For every 13 moles of O2 that I react, I'll be able to produce 8 moles of carbon dioxide. So it's just very simple dimensional analysis. So if I have 5 moles of O2, okay, I'm going to use these coefficients right here. So the reaction tells me that for every 13 moles of O2 that I burn, that I react, I will be able to produce 8 moles of carbon dioxide. Okay, and as per usual, my units cancel. That leaves me with moles of CO2. So 5 times 8 divided by 13 would give me, with 2 sig figs, 8.1 moles of carbon dioxide. So I'm still in moles, right? But now I'm in moles of carbon dioxide, whereas before I was talking about moles of oxygen. So this is just a one-step process, going from moles of one thing to moles of the other thing, and the only thing that I need are these coefficients from the reaction. Notice I didn't use all the coefficients, I just used the ones that pertained to my particular problem. Okay, so here's another example. How many moles of oxygen are needed to burn 8.5 moles of butane? So this is this kind of problem where I know how much of one reactant I have, and I need to figure out how much of the other reactant I need to make the reaction occur. So let's just dive into it. I have 8.5 moles of C4H10, and I want to know how many moles of oxygen I'm going to need to react all those moles. Well, again, I just use my ratio. And this says for every 2 moles of butane that I have, 2 moles of C4H10, okay, I also need, in order for the reaction to happen, 13 moles of O2. Okay, so what, 8.5 times 13 divided by 2 gives me 55 moles of oxygen that I would need to make that reaction happen if I want to burn all of these moles of C4H10. Notice that these coefficients do not affect my significant figures. These are ratios. They are not measured values, so they do not impact with sig figs. Okay, so that's how I go from moles to moles. Moles of one thing to moles of another thing. And again, I can go between reactants, between products, forwards and backwards between reactants and products. But that's keeping it fairly simple. As you hopefully know, you cannot measure moles. We do not have a scale in the lab that can measure moles. I can, however, measure other things like grams and volume. So ultimately, I'm going to want to get to those kinds of units if I want to be able to apply this in a lab scenario. So on Classroom for you, I have posted this beautiful little flowchart, or one very like it, that shows you how to make a whole ton of, well, like a whole web of calculations. Okay, so what we just did is this section right here. Okay, to go from moles of one thing to moles of another thing, I need the coefficients from a balanced chemical equation. Okay, but very rarely am I going to start with moles of something because, again, I can't measure them. This right here is the mole unit, right? You learned how to convert from moles of something to its mass, to its volume if it's a gas, to molecules or formula units if it's a molecular compound or an ionic compound. You learned how to break down those compounds into atoms, or how to go straight from moles to atoms using Avogadro's number, be it an element. Okay, so this over here is the same exact thing, just mirror image, and I said for B. All we've done in stoichiometry is added this connecting bridge that allows you to change substances. Okay, but here's the awesome thing is I can follow any path whatsoever that I want to convert from one thing to another. So let's say that I know how much mass of a reactant I have, and I want to figure out the volume of product that I can make if it's a gas. Well, that's going to be 1, 2, 3 steps. I need to convert from mass to moles using that thing's molar mass, and then moles of A, whatever that is, to moles of B using the coefficients in the reaction, and then I use the volume ratio of a gas to get to the volume of my product.